Let's get some practice working with these direction fields and looking at, just like we could create little solution diagrams from slope fields, we're also going to say, okay, what can we say about solutions from vector fields or direction fields? So we're going to start by, again, just kind of talking about our basic system. Let's say that we're considering some system of differential equations that we're going to call dy dt. And that'll be a vector of some function for x and y and some other function of x and y. And we're going to denote that with the vector valued function, capital F. And I want you to notice something here, right? Notice that this is, again, an autonomous system. And in fact, for all of the rest of chapter 2 and all of chapter 3, we're only going to look at autonomous systems. We're only going to look at systems of differential equations with no explicit independent variable. In chapter 4, we'll talk about systems that are not autonomous, but here let's just worry about autonomous systems. It's going to make plotting these things and doing some qualitative analysis a lot easier, but we'll eventually have to get into it in chapter 4 because, you know, surprise, surprise, a lot of real life models are not autonomous. So anyway, this is the general notation of what we're dealing with, right? There's some function that talks about how x is changing. There's some function that talks about how y is changing. And this is that vector notation that we're going to be using. Just like we often called the right-hand side f of y. Well, we're still calling it f of y, but f is now a vector valued function, and y is now the vector of the x and y component. Okay, so let's get some practice over here. So I want you to match the system. I give you 3 systems of differential equations. I want you to match the system with the vector field that corresponds to this. Now there's a couple of ways of doing this. One is to just evaluate a few different vectors here and see, okay, which ones follow the behavior. Another way of doing this is to kind of look at the behavior of the vector field itself and see which one of these might be the case. Either way, I do want you to pause the video. I know I haven't done any of these examples, but using both of those methods, either plotting your own vectors and seeing which ones match, or by looking at the behavior, I want you to pause the video and try to see if you can figure out which one is which. All right, so if we look at this first differential equation, notice that if x is positive, the rate of change of x is going to be negative, and vice versa. If y is positive, the rate of change of y is going to be negative, and vice versa. So if we're in the first quadrant, also notice that the rate of change of x only depends on x. The rate of change of y only depends on y. So lots of things that we could say for all of that. But specifically, if we're in the first quadrant, we should be decreasing in x and decreasing in y. So it can't be this. X and y are both increasing in here. It could be this, or it could be this. All right? Either one of these kind of matches that negative behavior, which makes sense, right? We have 2 differential equations that have that opposite behavior for these. So I guess that already tells us what letter C is. Also, I didn't actually write the letter C, but there it is. Okay. So yeah, I guess we know what C is. Right, this first one over here is letter C. All right. If x is positive, notice that the x, right, this tells us, and again, just give you a little reminder, right? This is dx dt. And this is dy dt. That's what dy dt means. It's the vector of the rate of change of x and the rate of change of y. So we see, yeah, in the first and fourth quadrants, if x is positive, the rate of change of x is just x. So yeah, these are all positive. And remember, there's no size here. These are direction fields. There is no size here. So even though x is increasing, these vectors are not getting longer. It's only the relative things. Okay. So now this is C. And then, okay, well, what's the difference between A and B? A and B are very similar. The only difference is the rate of change of Y. This rate of change of Y is going to depend a lot more on the Y value. In fact, it's going to depend doubly on the Y value. So as we change Y, which one of these has a bigger change? As Y varies, which one of these has a bigger change? The answer is over here, right? You can see over here, Y changes. As Y changes, the vectors only change a little bit. But as Y changes over here, the vectors change a lot more. So that tells us this one over here is B. All right, and again, there's many, many ways of answering this sort of question. You can also just plot your own vectors and see what behavior you get, and then match your behaviors to these. It will take a little bit longer, but you'll get there in the end. And we can also plot some solution curves, sketch some solution curves given some initial condition. What if I tell you that we have initial condition over here of, let's say our initial position vector is a vector 0, 0. Here I'm going to write this as a row vector. So we start at 0, 0 and follow the arrows. Oh, interesting. There are no arrows at 0, 0. We don't move anywhere over here, right? If X and Y are both 0, the rate of change is 0, 0. There is no rate of change. We're stuck here forever. Don't we have a word for that? We do. We'll talk about it in the next video. This is an equilibrium solution. In fact, all of these have equilibria at 0, 0. All right, right? They all have equilibria right there. Okay, well, let's look at what's another way that we can write an initial condition. We could also write an initial condition as x naught, y naught. Let's say we start at the point 0, 2. What happens in each one of these vector fields or direction fields? Well, over here, if we start at 0, 2, oh, we just stay on the y-axis. And we go up. Over here, if we start at 0, 2, what happens? Stay here and go down. And again, we don't know how fast we go up. We don't know how fast we go down. Direction fields have no concept of time. And again, over here, if we start at 0, 2, we also similarly go down. Again, we can plot a whole bunch of solutions. What if we have another starting vector? What if our starting vector is equal to, we should use a different color so we can actually show that these are different. What if x naught, y naught is equal to 1, 3? What happens? Well, 1, 3 is right here. Okay, over here we start going up. 1, 3. Oh, okay, we start going down. We approach the equilibrium over here. 1, 3, we go down much steeper, but it still seems like we approach the equilibrium. Interesting. Look at this equilibrium. It looks like things are kind of coming out of this equilibrium, that they're all getting pushed away from this equilibrium. Whereas over here, it kind of looks like things are all getting sucked, or they're kind of sinking towards this equilibrium. Wow, that's interesting. I wonder if we have a word for different kinds of equilibria. Who knows? We'll just have to keep going through this book, keep watching these videos. All right. But yeah, that's pretty much what we have. Again, reminder that there's no real concept of time. We don't know how fast these things are happening. But again, we can plot all sorts of solution curves depending on where we are. You're just following the arrows, right? What if you're over here? Well, you're just going to follow the arrows. If you're over here, well, you just kind of follow the arrows. The book has this weird metaphor of the parking lot. They said, imagine you're driving in a parking lot and there's a bunch of these arrows printed on the ground. You can go any speed that you want. We don't know. And you just follow the arrows. I don't find that particularly helpful, but follow the arrows. That's how you can look at solutions given a vector field or a direction field. That's pretty much it for this video. The next video we talk about equilibrium solutions, which may or may not have anything to do with these green dots in the middle. Anyway, talk more about that there. Hopefully you're kind of seeing what I claimed in the first video of this section, right? Is that this is all very similar to chapter 1. It's just the two-dimensional version. And of course we can extend this to n dimensions as we so please. It just gets harder to graph. We could do a 3-dimensional vector field. 4-dimensional vector fields are a little bit more complicated to visualize. And then, yeah, we go off the deep end real quick. But that's it for this. Bye-bye.